Welcome back. We are now working on chapter 12, and we'll be talking about identical particles. This is going to be the last screencast of this series. This chapter 12 is not completely covered compared to the book of Townsend, but we are going to cover a number of topics from chapter 12 and then focus then on identical particles that we have not done so far. So the main thing that we have to think about is that this concept of indistinguishability of particles in quantum mechanics is very different from what we know from classical physics. In fact, the point is all electrons are the same in the sense that there is no characteristic that can distinguish two electrons. They have exactly the same composition, exactly the same charge, and exactly the same behavior under any physical law that we know. So the question is, can we put a label on an electron? And the answer is no, we cannot. There is no label that we can put on electrons. Therefore, we cannot know if electron can be electron 1 or electron 2. So in classical physics, in fact, I would say in introductory physics courses, we sometimes see where we have two particles, 1 and 2, and they collide, and so from there we understand the properties of momentum transfer or energy transfer or total energy of the system, and we can still keep a label 1 or label 2 on the particles. We cannot do that for electrons in quantum mechanics. So this is an issue we have, and one reason to understand this is, for example, there is no way to know where an electron is. What does that mean? Well, it means that because of the uncertainty principle, we cannot know delta x exactly. And we cannot know exactly where particle is. So therefore, if we cannot know where particle is, particle 1 is, and where particle 2 is, then there will be places of overlap. There will be places where there is a probability of finding a particle, and we cannot know if this is going to be particle 1, particle 2. We'll see that in the next slide, where I have a plot of the overlapping probability density as we discussed starting from chapter 6. So this is where we are standing with this. So in classical physics, we have each particle has a well-defined position and velocity, but not in quantum mechanics. Okay, so classically the measurement a measurement is possible, and we do not influence the state of the particle, but this is not true in quantum mechanics either. So all those three points that I have on these slides relate to classical mechanics, but all the electrons are the same, and quantum mechanically we cannot distinguish them. So this is shown best on this picture here, which is comes directly from the book, where we have an overlapping probability density of particle 1, particle 2. So when we are measuring a particle, we have no idea if we are measuring particle 1, particle 2. So this notion of undistinguishability has profound effect on the properties of the particles and the properties of the kets and the state vectors that we can build from them. So in fact, this is surprisingly simple to understand things about physics from just the analysis of a simple operator that we are going to introduce in a second, which is an exchange operator. But before we go there, I'd like to talk to you about the two-particle state. So a two-particle state is defined in the red box there, is the direct product between the states of a particle 1 and the particle 2. So the way to read this particular ket here, the ket AB, is a ket that's created by the direct product of particle 1 being in state A and particle 2 being in state B. Most of the time we do not write the subscript 1 and 2, and usually in fact we write it simply as written on the left hand side, and we kind of lose the understanding of what this notation means. So please, if you have a trouble remembering what the notation means, so the left-hand side notation, remember that it's equivalent to the right-hand side notation, which is much more clear, but a little bit heavier. Therefore, physicists usually do not use the notation on the right-hand side, but it's actually much more clear that we see that particle A is in state 1 and particle B is in state 2. Okay. So let's try to, we are going to introduce an interesting operator, which is the exchange operator P12. And the P12 consists in changing the state of particle A and particle 2. In fact, it consists in putting particle 1 in state B and particle 2 in state A. So this is what you see in the first line there, and of course with the equivalent definition under. So this is nice because you see what you're changing is the state of each particle. So the first number, the first letter still corresponds to particle 1, and the second letter corresponds to particle 2. All right, so let's see what it does. So what we do here is just exchanging the two states. Now, if the two particles are not distinguishable, exchanging them should not change the state at all. And we know that two states are equivalent if there is only an overall phase factor between them. So in other words, if I have a state psi that's composed of two particles that are undistinguishable, exchanging them is equivalent to multiplying by an overall phase factor. Okay, so this is what we have there in the red box. The phase factor is EI delta, which is equal to lambda, let's say. So we are going to see what are the possible values of lambda. And of course, the usual idea is to probably to operate twice on that state. So if we do P12 square, this corresponds to exchanging the particle again and again. So clearly in that case, we understand that is essentially equal to the identity operator. And that means that lambda square has to be equal to 1. So lambda square has to be equal to 1, meaning that lambda can only be equal to 1 or minus 1. Okay? So remember here, I want to insist on this. This is not the square modulus of lambda. This is really lambda square. So it's lambda times lambda, not lambda times lambda star. So that means that lambda has to be equal to either 1 or plus 1, or minus 1, sorry. So lambda is equal to plus 1 or minus 1. So this is quite interesting that the effect of exchanging two particles correspond to changing the sign or not of the ket. So we can either change the sign or you don't change the sign in front of the ket. Now, in particular, if the two states are the same, so if the two particles are in the same state, so in other words, the one particle 1 is in state A, particle 2 in state A as well, exchanging the two states, of course, correspond to not changing anything at all, even when I just apply it once. In other words, that corresponds to lambda equal 1. Okay, so this is the only way we can do this. So in that case, we say that the state is symmetric on the exchange. Symmetric on the exchange means it doesn't change the sign. On the other hand, if we had the sign minus 1, we would then say that the state is anti-symmetric on the exchange. And so this is what we would get in this case. So we are going to see example of that in a second. Now, what's very interesting is now that we have an operator P12, and we already know what the eigenvalues of this state of this operator is. The eigenvalues are plus or minus 1, right? I mean, let's go back to this slide here. To this slide here, we see on the bottom right that P12, when he applies to a state to any state psi, get the same state psi times lambda, and we know that lambda can only be plus or minus 1. So that means that plus and minus 1 are the eigenvalues of P12. Okay, so but let's go a bit more general, calculate the matrix representation of P12. So when we talk about representation, obviously we are talking about representation in a basis. So we are going to use the basis A for AB, where particle 1 is either in A or B, and particle 2 is either in A or B. Okay, so one particle is in A, the other particle is in B. So that means that we can create the basis AB and BA, So these are the only two possibilities. And we can calculate then all the matrix elements. And very quickly we find that exchanging the particles because A and B are orthonormal, we automatically find that we have zeros on the main diagonal, right? For example, the first term, P12 applied to AB is VA. So that means that ABBA is going to be equal to 0. And P12, and then same thing around, and so on and so forth, right? So why do we have a 1 and not a -1, for example? Because P12 applied to BA is AB. And then we have AB is equal to 1. Okay? So here we have not used anything we know about the lambda that we spoke about before. We just replace AB by BA. Okay. Now, this matrix, of course, 0, 1, 1, 0, we know it very well. We know the eigenvalues of this very simply. The eigenvalues are +1 or -1. And this is what we get. And in fact, the lambda equal 1, we end up with eigenstate, psi s, which is fully symmetric for the exchange of particle A and B, as you can see. This is what the plus sign means in between there. And then we have the other eigenstate, which is psi A, which is anti-symmetric state, which is anti-symmetric for the exchange of particle A and B. And it's quite interesting to see that in that case, the lambda is equal to -1. So we have two eigenstates, psi S and psi A. One is symmetric under exchange and has an eigenvalue lambda equal 1. And the other one is anti-symmetric under exchange of particle A, particle 1 and 2, and has an eigenstate, an eigenvalue equal to -1. Okay? So far so good. So now we are going to show that a state has to be either symmetric or anti-symmetric. It cannot be a mixture of both. So far we didn't do anything special, but we want to show that a state of two particles, of two undistinguishable particles, is either symmetric or anti-symmetric. It cannot be the sum of both. Let's show that. Suppose that we have a general state that has a component along for the that's symmetric and a component anti-symmetric, so CS and CA. If I apply P12 to this, I do not change psi S and psi A, obviously, because, well, these are eigenstate of P12. But I change the sign for the second part, since the anti-symmetric state is anti-symmetric and has an eigenvalue -1 for the operator P12. So you see that the effect of P12 on that state that I built from psi S and psi A is not giving me a state that's just a phase factor difference. Okay? So we know that the effect of P12 on a two-particle state where the two particles are undistinguishable, we know that P12 applied to this should also give me the same state times maybe an overall phase factor. That was my definition I started with 4 slides ago. But clearly, in this particular equation I have on this slide, I cannot do that. I do not have that. I do not have P12 applied to a state is equal to the same state times an overall phase factor. In fact, this is only true if either CS is equal to 0 or CA equal to 0. In other words, I can only fulfill that condition if the state is fully symmetric or fully anti-symmetric. So this is quite amazing, I would say, because we did a very simple analysis of what we have, and yet we found of a two-particle system, and two undistinguishable particle system, I should say. And we find that the only possible state we have are either fully symmetric or fully anti-symmetric under exchange. So that means nature is only made up of such system. So nature has to choose between creating a fully symmetric anti-symmetric state, and the question is which one? Well, particle physics actually answer this question, but what we can say is that if the spin is integer we have a symmetric state, and this is a boson. And if S is half an integer, we have an anti-symmetric state. It's a fermion. This is the definition of fermion and boson. And in fact, for an electron would be a fermion, for instance. A photon would be a boson. So this is very important because the boson followed the Bose-Einstein statistical mechanics description, while a fermion follows the Fermi Dirac distribution for the statistics. So very different physics, very different observation, depending on the symmetric versus anti-symmetric system. So what happens if two identical particles occupy the same state? Well, you know the answer already. The state clearly has to be symmetric, because if it was not symmetric, then if it was anti-symmetric, clearly that's not possible, because if it's anti-symmetric and if you exchange the two particles, you would get a sign -1, but you can have a sign -1 if you have the same state. In other words, it's impossible. So we cannot do this for fermions. So in other words, fermions cannot occupy the same state. This is the Pauli exclusion principle. So the system has to be boson, and this is where the physics of Bose condensate and physics of that sort can come into play. Okay, so what we are going to do in this screencast is looking into the helium atom, and then we are going to look at it from two perspectives. The first perspective, we are going to use perturbation theory and explain that the two electrons in helium have to create this anti-symmetric state because they are fermions. And this anti-symmetric state combined with the use of perturbation theory, so time-independent perturbation theory, will help us understand observation for helium atom. So again, a very much quantum mechanical expression of the physics of undistinguishable particles. And we will end up this screencast with a description, an alternative description of helium atom using, not using perturbation theory, but using a variational principle. And we will conclude with that. The helium atom is a very good example of a simple system where we have two electrons together. So we have two electrons that live together in the potential that's created by the nucleus of the helium atoms, which is two positive charges. And so what's interesting here is that those two undistinguishable particles have to live together around the helium atom. And you will see that the fact that the wave function of the system has to be anti-symmetric, since we have fermions, that fact will lead to properties of the wave function and the energies. And so this is what we are going to do now. We're going to study the effect of this constraint, I would say, on the anti-symmetric nature of the wave function of the two electrons in the helium atom, and we'll see how it affects the energies and the states. We will look at two things. The first one, we will look at the ground state energy, and the second thing, we'll look at the first excited state. So for the ground state energy, we will, and for actually the excited state as well, we are going to use the time independent perturbation theory. And we will do that because we know very well what happens for a single electron around the helium nucleus. In fact, this is an exact problem, since this is a hydrogen-like system with Z equal 2. Anyways, we are going to do that. I hope it's going to be clear. It's going to be a little bit tedious when we get to the degenerate state for the excited state, but I think we can make it. Okay, so this is the Hamiltonian for the full system. This is an exact Hamiltonian. There is absolutely no approximations here yet. Of course, we are not taking into account spin-orbit coupling and things like that, but from a Schrödinger equation, this is exact. So we have the kinetic energy of the electron 1, kinetic energy of electron 2, and we have, of course, the attraction by the nucleus, and we have the repulsion between the two electrons. This is the last term. So we need to study this with z equal 2. Now, we are going to use a perturbative treatment. Why do we do that? Well, we do that because we can exactly solve H0. Okay? We can solve exactly H0, and when we write H0 the way it's written on the slide, we see that operators on the particle 1 and particle 2 do commute. In fact, they operate on different particles, or on different subspace, if you will, and that means that we can actually solve this problem exactly. This is a hydrogen-like atom. And then we use the perturbation E square over R1 minus R2, so the electrostatic repulsion between the two electrons, as a perturbation. So one thing that I'd like to highlight and really emphasize at this point is that H1 is not really a perturbation, in the sense that it's not necessarily small. H1 is not necessarily small. In fact, H1 is probably comparable to some of the other terms that are in H0 in terms of potential. But here we use a perturbative treatment because we know exactly how to solve H0, and we are going to see the effect of H1 on the state of H0. So we do expect that certainly at first order, certainly at 0th order, we are going to be pretty far away from the experimental values that we could find for the states of the helium atom. Even at first order, we don't necessarily expect to have very good agreement with experiment because, again, the perturbation H1 is not really a small perturbation. In any case, I'd like also to attract your attention, as always, that we have, for the signs, remember, negative signs mean attractive. This is the Coulomb interaction between electrons and the nucleus, and the positive sign for H1 means that we have repulsion between the two electrons. So the two electrons would try to get as far away from each other as possible, but at the same time they will be attracted by the nucleus. So let's see what we get from here. Okay, so this is the unperturbed Hamiltonian, and we can solve this exactly. Indeed, we really have the superposition of two hydrogenic states. Remember, this notation is actually a very useful notation where we have the direct product. The direct product simply means that we are considering an electron 1 in state N1, L1, M1 together with electron 2 in the state N2, L2, M2. So when I say a state N1, L1, M1, I mean it's a state that described by the principal quantum number N1 by the total angular momentum L1 times L1 plus 1 times h bar square, and finally the projection on the z-axis M1 h bar. So we know that these are the good quantum numbers we need to solve the hydrogen atom, a hydrogen-like atom. Remember, we were carrying the z, the number of protons all around. For hydrogen, of course, z equal 1. And we can do that for both electrons. And now, because we can separate the variables, the full state for H0 is simply the direct product between the state for electron 1 and the state for electron 2. And H1, of course, is the repulsion between the electrons. Okay, so for the ground state, clearly for the ground state of the full system, we are going to build that ground state from the ground state of the two electrons in the helium nucleus. So this is the ground state is obviously n equal 1, and L equals 0, and M equals 0, of course. So this is the 1s state, right, for the hydrogen atom. The notations, sometimes we drop the direct product, it's implicit. This is just a notation thing. Now, this state is the exact ground state of the Hamiltonian, since we can separate the two particles. The two particles do not interact. There is no cross term, right? So we just have to make sure that the state is anti-symmetric under exchange of the two particles. Remember, these are fermions. However, if I replace one particle by the other, I mean, if I exchange the two particles, clearly the state that I just created there is symmetric. So it's not good, right? So what happens? How can we make it anti-symmetric? Well, we make it anti-symmetric by introducing the spin. So we have by making sure the spin part of the wave function is anti-symmetric. That way, a symmetric state times an anti-symmetric state will be anti-symmetric. So what does that mean exactly? We have two electrons, two spin 1/2 together. Go back to chapter 5 to remember what we did. And we want to have a total spin, in this case, total spin of 0 and a projection of 0. And this state that we looked at is the state that's written there on the bottom right corner of this slide. And what we see here is that indeed that state is anti-symmetric. He has a total spin of 0 and a projection of 0. This is a state that we looked at when we looked in chapter 5 in the combination of two spin 1/2. Okay? So remember that we in principle, I mean, the way to understand how we build this state here is the fact that we can separate the variable. We can separate the spin variable, we can separate the position variable. That's the reason why the full wave function, in fact, the full ket in this case, it's not a wave function yet, but this formal object here is simply given by the product, or in fact, the direct product between all those properties. The point, though, is that if I exchange particle 1 by particle 2, I see that this state that I just built there on the slide is anti-symmetric. So if I just swap them, they're going to be anti-symmetric, which is exactly what I want, exactly what I need. And we write this state 1s, 1s, because clearly the two electrons separately are in a 1s state. Okay? Good. We can also write it 0, 0, same difference for the spin part. And this state is an eigenstate of s squared with eigenvalue 0, and of course projection 0. This is the only possibility we have for a total spin 0. Okay, we've seen that chapter 5. Good. Now, we see that something very interesting is just even though the Hamiltonian does not have anything to do with spin whatsoever, right? There's no spin interaction, there's no spin orbit coupling, there's no hyperfine whatever. There's nothing like that in the Hamiltonian explicitly. Because of the constraint of the anti-symmetry on the ket due to Pauli's principle, I would say, because of that, the total spin of the system is imposed by symmetry. So the total spin of the system has to be 0. Okay? In fact, it does not just has to be 0, it has to have exactly the shape that we have there in the middle of the slide. So this is something that's very important to understand in quantum mechanics, is that we do have a number of constraints that lead to some physical properties that are imposed by those mathematical constraints. And in fact, one of the art of doing quantum mechanics is to be able to impose those constraints and see how they affect the physical properties that we can measure. Okay, so we have this state. Again, this is a fully anti-symmetric state upon exchange of particle 1, particle 2. And this is usually written spectroscopic notation 1 as 0. The 0 means that we have a total spin of 0. And for the energy now, we can calculate the energy of this state very easily. This is going to be the sum of the sum of the energy of the two electrons that interact with the two protons. And of course, we know that exactly. So the factor of 2 in front of the equation there comes from the fact that each electron counts. The next terms that we have is the term that we found that is minus 13.6 eV when z equal 1, right? This is for the ground state of the electron. So we see that this value in parentheses is in fact 4 times 13.6, since we have z squared, 2 squared. And then we end up with a total energy of minus 108.8 eV. So this interaction is this energy is the energy of two electrons that do not interact with each other, but interact with a nucleus of charge plus 2. Okay. Now, we know that the first order perturbation consists in calculating the expectation value of H1 for that particular state 1s, 1s. And we know how to do that. Of course, we know exactly what the state 1s, 1s is, because we calculated that for the hydrogen-like atom. So we can calculate this term, and we calculate this term by doing the following. So we are going to write the full symmetric state this way. So we are actually writing the full symmetric state this way, which you can recognize as the identity operator that actually applies to psi s. That's the identity operator that's written in a symmetric way. And of course, for the symmetric state, I know that if I have a symmetric state in terms of the Cartesian coordinates, not in terms of the spin. Here, the spin is not included yet. So it's symmetric. We know that, right? We know that the ground state is symmetric. That's how we decided it to be symmetric in terms of the position state, of the Cartesian coordinates, not in terms of the spin, which is anti-symmetric. So when we do that, of course, we know that the wave function, so the R representation, is symmetric. And we can calculate, of course, psi s, and we find, again, another expression for the identity operator for the basis R1, R2. So nothing really surprising here. So now, of course, we can calculate the expectation value of H1 for that particular state. And of course, the spin part we don't have to worry about because there's no explicit spin part in H1. And we end up with something that looks like this. That's pretty obvious. We have the density, the charge density, so the probability density of finding the particle at between R1 and R1 plus dR1 times the probability density of finding the particle at R2 plus dR2 multiplied by E squared over R1 minus R2. Okay, this is something that comes directly from the calculations, and we have not done it explicitly yet. So if we write the probability density just this way, okay, this is really a probability charge density because we have E in front. And then we see that we can rewrite the whole thing in terms of a potential to the charge at R2. So this is the potential that we have right there. And that means that we can rewrite the terms the energy at first order using kind of something that we understand a little bit better, in the sense that we see that we have it's the interaction, the electrostatic interaction between a charge density at R1 times a charge density at R2, which makes sense. It's a classical interaction between two charges, two cloud of charges positioned at two different places. So you see we have this interaction. And again, remember that this term is for the charges that are located in the state of the hydrogen atom, so the unperturbed state in the interaction. And the bird you hear is a bird that's actually doing his nest on the window of my office, and I don't want to perturb it. It seems to be willing to hear some quantum mechanics, and I'm not going to perturb it because this is great to do quantum mechanics for a bird, I guess. Okay, so we can calculate this. Again, how can we calculate it? We calculate it because we know exactly the analytical form of the wave function, and we find that this term is actually 34 eV. I say not an obvious result in the sense that we need to perform the integral, which I have skipped here. But the point is, this is an exact result for the first order perturbation. Okay. Now, what we see from this too, we see that that this term is of course positive. Why is it positive? It's repulsive. It's the fact that the two charges interact with each other in a repulsive manner. Remember, the two charges have the same sign. Now, the energy at first order now is given by minus 74.8 eV. Experimentally, the value is minus 79. So here we can say, oh, it's pretty good, right? Well, it's actually pretty good in the sense that we are just within about a bit less than 10% error. But it's not great in the sense that we are still quite far from the experimental value. But again, this is surprising that we get so close to the experiment, given the fact that that interaction between the two electrons is certainly not a small value. Look, just from this calculation, we find that the first order correction is 1/3 of the energy we started with. So this is certainly not a small perturbation that we have here. But already we have we understand the origin of all the terms by just looking at the interaction between two clouds. Remember that here, at first order, we have not modified the state. We have just used the state as if they were from the hydrogen-like atom. So this is quite surprising that we have something like this. In fact, we are still above the energy. We are not as stable as the experimental value. We overshot because the fact that the two charges are interacting in a repulsive manner should push them away from each other and therefore stabilize the system. That's what will happen at second order. So we don't have this in this term, but we still understand, we start to understand the physics a bit better already. Now we're going to look at the first excited state for the helium atom, and we'll see this is a bit more complicated problem because the first excited state means that, at least if we start from the hydrogen-like atom, one of the two electrons has to be in an excited state of the hydrogen-like atom. The problem in that case is that we have a degenerate state. Okay, we know that for n equal 2 we have the degeneracy of 4 n square, so it's n square, so the degeneracy is 4. Then that means that we have to use the perturbation theory for a degenerate state. Okay, so that's what we're going to do. So we know that there are four possibilities to create the first excited state. One of the electron will be in the ground state, and the other electron will be in an n equal 2 state. So one of the four n equal 2 states. Remember, for n equal 2, we have a state L equal 0, L equal 1, and for L equal 1, we have three states: m equal 1, m equal 0, m equal minus 1. So that means that we are going to build these four states here. Lots of notations. Don't be scared by that. This is no big deal. The notation is simply giving L, N, L, M, and then the spin. And you see that those states have already been built such that they're anti-symmetric. So we have no problem with the exchange interaction. I mean, not exchange interaction, the exchange operator. If we swap electron 1, electron 2, we have an anti-symmetric state for all those four states. So these are just built, I would say, naively by having one electron in the ground state and the other electron in the excited state, and then anti-symmetrizing the thing. Okay. Now we see that the first two states there, we can factor out the spin part, right? We can factor out the plus z1 plus z2, and that means it's an eigenstate of the total spin. In fact, it's an eigenstate. It's absolutely an eigenstate of the total spin. The second one, we have the same thing for minus z. Now we cannot do that. We cannot factor out the plus z minus z state, or plus z for the two particles for the last two equations. So that means that if we want to build states that are also eigenstate of the total spin, remember the total spin operator, of course, commute with the Hamiltonian, since the Hamiltonian does not explicitly depend on the spin. We certainly want to create eigenstate that will be also eigenstate of total spin, right? Remember what we always do when we have a commutator between two operators, and the commutator is 0, then we can choose the state to be eigenstate of both. Okay, so this is what you see from looking at this. So again, one thing that students are usually confused about is notations. That's a lot of numbers, a lot of words, but at the end of the day, it's all very logical, and it's just have to be systematic and be good at bookkeeping. Okay, all right. So the unperturbed energy for those states is easy to calculate again, because it's just the energy of one electron in the ground state and the energy of an electron in the n equal 2 states. And we know the energy is given by minus 13.6 times z square over n square. And so that's what we end up with, minus 68 eV. So the perturbation now, we have to calculate H1 in the subspace that we just described with the 4 state and diagonalize it. We have a 4x4 matrix, and we of course can do a brute force treatment, or we can use symmetry argument, so that we can make sure that everything works out at the end. And this is, of course, we are going to use the second one, no brute force. It's much easier to think a little bit more. We know that H1 and H0 commute with the exchange operator. They have to be. Clearly, if we are replaced particle 1 by particle 2, I do not change the Hamiltonian. That's the idea. Okay. Neither are Hamiltonian, H1 or H0. And in fact, we can also think about the exchange operator as operating on the spatial coordinate, on the spin coordinate. And we need to have both commutator between the spin coordinate, exchange of the spin coordinate, and the exchange on the spatial coordinate. So we want to certainly find states that are eigenstate for the two exchange operators at the same time. Okay, so these are the 4 states I had before, and now we want those 4 states to be also eigenstate of the two exchange operators that we want. So clearly the first 2 are already like that, right? They're already eigenstate of the replacing 1 and 2. The last 2 are not. In fact, the last 2 are not. So what I mean by are not, they are not eigenstate of the spin, the p12 spin and the p12 spatial. But we can use a linear combination of them. And the linear combination of them then now is actually good and gives us something that we want. It's also at the same time also an eigenstate of the total spin operator. In fact, it's the 1,0 state for spin. The total spin is 1 and the projection is 0. This is the state that we have used all the way in chapter 5 when we were talking about entanglement. This is a typical state that we use for entanglement between 2 particles. This is right there, the right hand side, the spin part. If we do 1 minus 2, we get another entangled state, and that state is actually a total spin of 0 with a projection of 0 as well. So notice the minus sign. So now we're in good shape because we have those 4 states that are also eigenstate of the spin operator, but also of p12 spatial and p12 spin. Okay, so these are the 2 states that I just mentioned before. So this is exactly what I had before, but now in a more, these are the 4 states, but written in a more synthetic way with an m operator, an m number that I can actually change. That's just goes from -1 to 1. Okay, so we have, of course, also an additional symmetry, which is the rotation of the entire system. So in other words, that means that the Hamiltonian must commute with the angular momentum operator, the orbital angular momentum operator, which is L. And so the eigenstate of H1 are also eigenstate of L. In other words, the L is well defined. Okay, so as we said, one of the particle of the in the states, all those states is in a state with L equals 0. That was the ground state of the Hamiltonian, and thus the states are all eigenstate with the total orbital angular momentum L and projection M. Right? This is what we are doing here. One of the particle is in state L equals 0. The other particle is in state L equal L. Therefore, the total system is a total angular momentum L and projection M. This is something that's important to notice, and then that means that they're also eigenstate of L, so that's all good. So that means that now we can calculate the shift in energy as obtained by simply this matrix element right there. Actually, the set of matrix element that we have. Remember, this is 4 by 4, but they can all be written this way right here. So that's all good. We have to calculate this, and this is actually an integral that can be calculated by just distributing. This is a little bit, again, you have to pause the screencast and do it on a piece of paper. There's nothing really complicated here. It's just that we have a lot of terms coming from the integral. But what we end up doing, and we end up working with the sum, the fact that we have those plus minus at the end of the day, lead us to have 2 terms. And this is what we see. We have two separate integrals right there. So let's try to see where we get, at the end of the day, the 2 part of the integral, we have what's called J, and another one that looks like that's called K. And the energy shift due to this, the energy shift due to the perturbation H1 is actually a sum of 2 terms, J and K. Okay, so what's interesting to notice is that J is actually very much the same thing as we did for the ground state perturbation. We have a charge density at R1 and a charge density at R2. So the first term is a classical term, I would say. It's a classical term between interaction between 2 charges. Okay. Now here's the thing that's very interesting. The second term is not classical. The second term cannot be explained by a charge density times charge density. This is something different. And it's come completely from the fact that we had to have an anti-symmetric state. So the other term is really an exchange type of energy, and it's purely quantum mechanical. So let's try to go a little bit further than this. It turns out that J has to be positive. I hope you see that. I mean, you only have positive numbers that we integrate, so it's going to be positive. And this is really the repulsion between the electrons. Not really surprising. We had the same for the ground state. Now, K can be shown, I mean, without the plus minus in front. The K is actually a purely positive number. We can actually argue why it is. In fact, it's purely positive because it turns out that it comes from the exchange of particles and the fact that the two particles cannot be at the same place at the same time, right? This is what it means, not being at the same state. The two particles, by Pauli principle, exclusion principle, they cannot be at the same place at the same time. Therefore, that particular interaction, the fact that they have to be anti-symmetric upon exchange for the two particles, lead to the fact that the electrons, by not being at the same place at the same time, that stabilize the system. Because of course, if they were very close to, infinitesimally close to one another, that would in fact raise the energy significantly, right? Because it's repulsive. But K in terms is a stabilizing factor that is due to the fact that the particle cannot be at the same place at the same time. So this is actually a stabilizing factor. It's the exchange energy that we have. Okay, so we can calculate this E1 just the same as I showed before, and this is exactly what I explained now, that when the first line would disappear for the anti-symmetric solution in space. So so the electron, another way to say what I just said is that the electron in the anti-symmetric spatial state, they tend to avoid each other in space, and this lowers the energy compared to the symmetric spatial state. So clearly we have in the anti-symmetric state, we have a stabilizing factor due to the fact that the two particles cannot be at the same place at the same time. Okay, this is called an exchange term, and it provides an energy shift that's related to the fact that we have an anti-symmetric system in space, and so that means that depending on the value of the spin, the total spin, we have either an stabilized or destabilized solution. So instead of having 4 degenerate states, some get stabilized and the others don't get stabilized. In fact, the high spin states, so the spin equal 1, is stabilized, while the low spin equal 0, is raised in energy. That leaves the degeneracy, about between those 4 states. Okay. So I would like to conclude this screencast by discussing how we actually usually calculate the ground state or actually any eigenstate of a system for which we cannot find a full analytical solution. So we discussed about perturbation theory, which works well, as we have seen for helium. There is another method that's called the variational method. So I'd like to introduce to you the starting point for the variational method and show you how it works well. It works particularly well when you want to apply this numerically, and let's do that. Okay. So before we go anywhere, let's talk about the expectation value of the energy, which obviously is given by this for any state psi. Okay, that's any arbitrary state psi that correspond to a realization of the system that we are looking at. Now we know that in principle we can always write any state using the basis of the eigenstate of the Hamiltonian. Because that the eigenstate of the Hamiltonian form a complete basis, so we can certainly use that to describe our problem. Of course, we don't know that basis. If we knew it, we would have solved the problem, but in principle, we can write it this way. The coefficient Cn, just the projection between psi and En. Again, we don't know that either, but in principle, we can write it anyways. So in other words, we can write that the expectation value E can be written in terms of the energy, the energy of the eigenstate, and of course all the energy of the eigenstate are at least equal, but usually larger than E0, where E0 is the ground state energy. So since we have a complete basis, the sum over n of the Cn square is equal to 1. This is the normalization condition. In other words, the expectation value is always larger or equal of the ground state energy. So what I mean by that is that this energy, the expectation value, if we could calculate it for every single state possible, we would know that if we pick the state, if we found the state that was the ground state, then that expectation value would be minimal and would be E0. So this is why we call this a variational principle. The idea is to find a way to vary the states, to sample the states, psi, and take the state that is actually the lowest energy that you can find. And that state will be a good approximation of the ground state energy. That's the idea. So this is a very simple procedure to do, especially numerically, but we can also do it analytically if we have a certain space, a parameter space that we can use, okay? So this result is very important, is that the ground state energy will be always the minimal value of this expectation value for any state psi. This is, of course, become a minimization problem that we have to solve. So in practice, we usually use a trial wave function, and we hope that that trial wave function will be a good approximation for the actual ground state. So we try to use physical intuition to start with this. Okay. So for example, in the case of helium, a good example of the spatial part of the ground state would be given by the direct product between a state of electron 1 in an hydrogen-like realization and electron 2 in a other ground state of the hydrogen-like ground state. Now, here is the thing. Here we have a parameter we call Z tilde, which is the effective amount of charge. So remember, all those ground states that we looked at for the hydrogen depended on Z. So here we can say that Z would be an adjustable parameter, as just because we could maybe use this as a parameter that we could adjust a little bit the wave function. So the idea would be, of course, to try to find a wave function that minimizes the energy. So if we do that, and by the way, this state is, of course, symmetric for exchange, and the anti-symmetric part will be taken care of by the spin part, which we don't have to worry about in this case. All right. So, of course, we know what is the R representation of those states. We know that very well. It's just simply an exponential, a decaying exponential with a coefficient that is Z tilde. So the larger Z tilde, the smaller the distance at which this will actually decay. All right. So Z tilde is a parameter to determine. And in fact, we can calculate this by using the expression of psi that we had on the previous slide and using this Hamiltonian, the full Hamiltonian, of course. And we find that we can rewrite this Hamiltonian. So here it's kind of a trick to do this. We can rewrite the Hamiltonian so that we can solve it exactly for hydrogen-like atom of charge Z tilde. And so we can calculate this. This is like two hydrogen-like atoms. And we find that once we solve this, that we get an expectation value of the energy that's provided analytically that only depends on one parameter, which is Z tilde. And now, of course, we can minimize that energy with respect to the parameter Z tilde by calculating the first derivative of E with respect to Z tilde. And we want to minimize it. And we find that the minimum will happen when Z is equal to Z tilde minus 516. Turns out, when I invite you to do this calculation, it's a very simple calculation to do, of course, because we have just a second order polynomial to derive. I think you can do this. And you find the minimum at the effective charge, Z tilde, which is the Z for helium, which is 2 minus 516. So it looks like there is actually a screening of the charge of the nucleus by the other electron. So it looks like each electron on average, instead of seeing two positive charges, sees two positive charge minus 516. It is due to the presence of the other electrons around. So this is an effective charge. And of course, when you do that, you end up with an energy that you know that energy is the minimum for this particular model, right? And in fact, we find that we can kind of have an upper bound for the ground state energy. In this case, we find it's minus 77.4 eV, and a very simple model. Remember, the experimental value is minus 79, so it's very close to we are doing much better than this perturbation approach. And of course, this is a very attractive method because numerically, minimization problem numerically, even with more than one parameter, is actually something that's very easy to do on computers these days. So this concludes the screencast on chapter 12, and in fact this concludes the screencast for this course. I hope that you have enjoyed this course, that you have learned quantum mechanics from a perspective of operators and starting from Stern-Gerlach experiment. And stay tuned for more screencasts. Thank you.